Welcome to today's paper reading. Today's paper is titled Memorag, Moving Towards Next-Gen RAG via Memory-Inspired Knowledge Discovery. This technical report was authored by Hongjin Qian and colleagues from Beijing Academy of Artificial Intelligence and Renmin University of China. The existing Retrieval-Augmented Generation (RAG) systems face limitations in handling tasks involving ambiguous information needs or unstructured knowledge. To address these issues, the authors propose Memorag, a novel retrieval-augmented generation paradigm. Memorag features a dual-system architecture, utilizing a light but long-range LLM for global memory formation and an expensive but expressive LLM for generating the final answer. This framework is further optimized by enhancing the cluing mechanism and memorization capacity. Experimental results demonstrate Memorag's superior performance across various tasks, including those where conventional RAG systems fail. The Memorag framework is a novel approach designed to enhance the capabilities of large language models, LLMs, by addressing the inherent limitations of traditional retrieval-augmented generation, RAG, systems. Memorag introduces a smart interface that connects tasks with relevant knowledge from a database, enabling the generation of factual responses based on a knowledge-grounded context. A key feature of Memorag is its memory module, which generates retrieval clues that reveal underlying information needs for a given task. These clues are used to effectively retrieve necessary knowledge from the database. The framework employs a dual-system architecture, utilizing a cost-effective, lengthy and context-light LLM as the memory and a heavy LLM for retrieval-augmented generation. To evaluate its effectiveness, Memorag was tested using the ultra-domain benchmark, which includes complex RAG tasks with long input context from diverse domains. The results demonstrate that Memorag outperforms conventional RAG methods in tasks requiring implicit information needs, distributed evidence gathering, and high-level understanding of the entire database. Additionally, Memorag remains competitive in traditional question-answering tasks, where its clue-based retrieval approach offers significant advantages. Figure 1 illustrates the contrast between standard RAG and Memorag in handling queries that require a deep understanding of the entire database, using the Harry Potter books as an example. On the left, standard RAG faces difficulties in accurately pinpointing the necessary evidence due to the implicit nature of the query, leading to a less accurate response. Conversely, on the right, Memorag builds a global memory across the entire database. Upon receiving a query, Memorag initially recalls pertinent clues, facilitating the retrieval of useful information and consequently producing a precise and comprehensive answer. Memorag introduces a memory model, MEM, which acts as a semantic bridge between the input query and the database. This model establishes a global memory of the database, enabling efficient processing of long contexts. The staging answer, Y, serves as a set of answer clues that guide the retrieval process, and its form is tailored to the specific task requirements. The system implementation includes 2 released memory models and employs token compression for efficient context processing. Memorag also supports flexible retrieval methods and can integrate various generative language models. The memory module in this paper is designed to facilitate memory formation in large language models, LLMs. The input consists of N tokens, which are processed by a transformer-based model using an attention mechanism. To transition from short-term to long-term memory, memory tokens are introduced. These tokens are appended after each context window, and special weight matrices are used for their interaction. The process involves maintaining a KV cache for previous tokens and converting raw tokens into memory tokens, simulating a human-like memory formation process. The memory module in Memorag involves initializing a set of weight matrices, WQM, WKM, and WVM, specifically for mapping memory tokens into query, key, and value vectors. These matrices are updated during training, while the underlying large language model, LLM, parameters remain unchanged. The training process is divided into 2 stages: pre-training using randomly sampled long context from the Red Pajama dataset, and supervised fine-tuning, SFT, with task-specific data to generate task-specific clues. The training objective is to maximize the probability of generating the next token, considering the KV cache of previous memory tokens and recent raw tokens. The Memorag framework begins by transforming the input sequence X into a compact memory representation XM, which captures high-level semantic information from a global perspective. This memory is then used to generate task-specific clues Y, which help outline the expected answers Y, bridging the gap between the raw input context and the ground truth answer. Finally, the framework retrieves precise evidence text and generates the final answer Y using a generative language model, leveraging the underlying model of the memory for generation. Memorag expands the applicability of standard RAG systems by addressing several complex information needs. For ambiguous information needs, Memorag uses global memory to infer the underlying intent of implicit queries and generate staging answers to bridge the gap. In handling distributed evidence queries, Memorag's global memory capabilities allow it to manage multi-hop reasoning by integrating information across multiple steps. For information aggregation tasks, Memorag leverages global memory to synthesize key points from the entire dataset, producing comprehensive summaries. Table 1 illustrates how Memorag handles implicit queries by forming a global memory across the relevant database and generating key answer clues that facilitate the retrieval of relevant content. For instance, the input query "How does the book convey the theme of love?" lacks a direct semantic connection with the content in the relevant database, as the theme of love is not explicitly stated in the raw text. Memorag forms a global memory across the entire database and generates key answer clues that facilitate the retrieval of relevant content from the database. The clues include Lily Potter's sacrifice, the Weasley family, and romantic relationship with Ginny Weasley. These clues guide the retrieval process, allowing Memorag to generate a comprehensive answer that highlights various key moments and relationships in the Harry Potter series, illustrating how love, in its many forms, is a powerful and recurring theme in the narrative. Table 2 illustrates how Memorag processes a query requiring distributed evidence. The query "which year had the peak revenue in the past 3 years?" is addressed by analyzing financial data from the past 10 years of a large company. Memorag breaks down the query into surrogate queries for specific years, 2021, 2022, 2023, and integrates the results to determine that year 2021 had the peak revenue. This example showcases Memorag's capability to handle complex, multi-hop queries by reformulating them into manageable parts and aggregating the findings to provide a precise answer. Table 3 demonstrates how Memorag processes an information aggregation task by summarizing a government report on city construction. The task involves extracting key points such as infrastructure development initiatives, budget allocations and expenditures, and future urban planning and zoning. Memorag then retrieves detailed content and aggregates this information to produce a comprehensive summary of the report, highlighting significant infrastructure projects, financial details, and future planning strategies. Table 4 illustrates how Memorag handles a personalized recommendation query. When asked, "Can you recommend a song for me?" Memorag analyzes the user's dialogue history, identifying preferences for certain music genres, artists, or eras, and uses this information to suggest a song that fits the user's profile. For instance, based on the user's preference for jazz music, fondness for 1980s music, and knowledge background in music theory, Memorag recommends Take 5 by Dave Brubeck, a classic jazz piece from the 1960s that aligns with the user's preference for jazz and appreciation for music with complex structures. Table 5 demonstrates how Memorag handles a query with omitted semantics in a conversational search context. The query, "Does it have any weaknesses compared to the paper we discussed last Monday?" is processed by generating a surrogate query that clarifies the omitted details. The surrogate query, "What are the weaknesses of this paper compared to the ABC paper?" is then used to retrieve relevant information. The answer highlights the research paper's weaknesses, specifically limitations in the methodology and gaps in the data analysis. This example illustrates Memorag's ability to accurately interpret and respond to queries that depend on prior conversation context. The evaluation of Memorag in question answering, QA, and summarization tasks involve the use of 13 existing benchmark datasets. These datasets cover various types of QA tasks, including single-document and multi-document QA, as well as summarization and logbook QA tasks. To further assess Memorag's capabilities, the ultra-domain benchmark was constructed, which includes tasks with long contexts and high-level queries across multiple specialized domains. Additionally, 2 specialized datasets were utilized: the FIN dataset derived from financial reports and the legal dataset from legal contracts. Furthermore, 428 college textbooks spanning 18 distinct domains were collected to test Memorag's versatility across a wide range of topics. Table 8 provides a detailed overview of the datasets used in the evaluation of Memorag. It includes the number of samples, average length in tokens, and the evaluation metric for each dataset. For instance, the Hotpot dataset has 200 samples with an average length of 18,409 tokens, evaluated using the F1 metric. Similarly, the legal dataset contains 438 samples with an average length of 51,413 tokens, also evaluated using the F1 metric. This table is crucial for understanding the scope and complexity of the datasets that Memorag was tested on, highlighting its capability to handle diverse and extensive text contexts. Table 9 provides a detailed statistical overview of the out-of-domain evaluation datasets used in the study. Key metrics include the maximum context length, max-C, which reaches up to 1,071,342 tokens, indicating the extensive length of documents analyzed. The average context length, (AVC), is 150,684.0 tokens, reflecting the substantial textual depth required for these tasks. Additionally, the average answer length, (AVA), is 48.5 tokens, highlighting the complexity and detail expected in the responses. These statistics underscore the breadth and depth of the datasets, which are crucial for evaluating the model's performance across diverse and extensive textual domains. Table 6 presents the main experiment results on the ultra-domain benchmark using the Mistral 7B Instruct V0.2-32K model as the generator. The evaluation metric used is the F1 score, with the best results highlighted in bold and the second best results underlined. The upward arrow indicates the improvement over the second best results. The average context length, denoted as AVC, is counted in thousands of tokens K. The table details the performance across various domains, both in-domain and out-of-domain, showcasing the effectiveness of the Memorag model in handling diverse and complex tasks. In this section, we compare Memorag with several baseline methods. The first baseline involves directly feeding the full context into large language models, LLMs, to fit their maximum length. Another baseline is BGM3, a general-purpose retriever used in standard RAG. Stella and 1.5 BV51, a top-ranking model on the MTB leaderboard, is also included in our comparison. Additionally, we evaluate advanced techniques such as RQRAG, which refines queries for better retrieval, and HIDE, which generates fake documents for passage retrieval. For a comprehensive comparison, we employ 3 popular LLMs as generators: Llama 3-8B Instruct 8K, Mistral 7B Instruct V0.2-32K, and Phi 3 Mini 128K. The ultra-domain benchmark consists of 2 types of datasets. The first type includes 3 in-domain datasets with context sizes under 100K tokens. The second type includes 18 out-of-domain datasets sourced from English college textbooks with context lengths up to 1 million tokens. Memorag demonstrates superior performance across all datasets, outperforming all baseline models. This indicates its strong domain generalization capabilities. Additionally, Memorag effectively handles long contexts and complex tasks, consistently surpassing the performance of directly using the full context. This highlights its ability to bridge the gap between processing super long contexts and addressing complex tasks. Memorag also shows superior performance on the 3 in-domain datasets, suggesting that its potential can be further enhanced with more diverse training data. Table 7 presents the main experiment results, highlighting the superior performance of Memorag across multiple benchmarks. The table showcases Memorag's ability to outperform all baseline models, particularly in open-domain question-answering tasks and summarization tasks. Notably, Memorag demonstrates significant improvements in domain-specific tasks that involve long contexts, such as financial and legal datasets. This performance underscores Memorag's effectiveness in handling complex tasks with extensive textual data, positioning it as a robust solution for knowledge-intensive applications. The experiment results, as shown in Table 7, indicate that Memorag generally outperforms all baseline methods across various datasets. Specifically, in open-domain QA tasks, Memorag demonstrates improved performance on all datasets except for en.qa when using Llama 3 as the generator. This improvement is attributed to Memorag's ability to more effectively locate the necessary evidence within the original context. Additionally, for domain-specific tasks such as financial and legal, Memorag shows significant enhancements, highlighting its capability to manage complex tasks with extended contexts. These results collectively underscore Memorag's robust performance and general applicability across different query types and datasets. In this paper, the authors introduced Memorag, a novel retrieval-augmented generation (RAG) system designed to integrate global context awareness. This system features a memory module that constructs a compact global memory across the entire database, enabling the generation of context-dependent clues. These clues effectively link the knowledge database to the precise information required for accurate answers. Extensive experiments demonstrate that Memorag significantly outperforms traditional RAG systems in tasks such as knowledge-intensive question answering, summarization, and handling real-world applications involving lengthy documents. Memorag excels in tasks requiring advanced information aggregation and shows exceptional robustness and versatility in managing large-scale texts like textbooks, financial reports, and legal contracts. It can handle contexts of up to 1 million tokens and resolves complex queries with superior accuracy. Thank you for watching.